adding HCl. Does HCl contain hydroniums or hydroxides? It does not. But we know that HCl will react with water to make hydronium ions and chloride ions. So if I add HCl to water, hydronium concentration will increase, hydroxide concentration will decrease, and the pH will go down as a result of the higher hydronium concentration. You have to keep reminding yourself about the idea that the pH scale is kind of upside down. Right? pH scale is a measure of hydronium ion concentration. Yes? The negative of the base 10 logarithm. But put a negative sign. It is, but I drew a one-way arrow to get to our next point. Okay. Now, if I add sodium carbonate to water, first of all, is it soluble?
Yeah. All carbonates.
The solubility rules say all carbonates are insoluble, except the ones with the alkali metal ions. Or we have another rule that says anything with the alkali metal ions in it is soluble, right? So this is soluble. When it dissolves, it dissolves to form sodium ions and carbonate ions. Yeah?
Ooh, just base.
And then, as we just wrote a minute ago, the carbonate ions can take hydrogen ions away from hydronium ions. So carbonate ions can affect the pH by taking hydrogen ions away from hydroniums. And if you take hydroniums away, the hydronium concentration goes down, the hydroxide goes up, and so does the pH.
So, when you like sodium, that was like assuming we added it in water.
Yes.
And then the products of that would be the carbonate, which takes away hydrogen from the hydronium, which increases the hydroxide.
And you're not going to ask me where the hydroniums are in the water, right? Because water always contains hydroniums and hydroxides, doesn't it? Right? Now, one more step. What happens when I add this to water? Well, first of all, when I add copper chloride to water, it dissolves to form copper plus 2 ions and chloride ions, right? What can chloride ions do? Can they act as a base? Any negative ion could be a base, couldn't it? So, chloride ion, how strong a base is it? Really weak, right?
Yeah.
We don't expect chloride ions to grab hydrogen ions away from hydronium ions, do we? Carbonate ions did that because they're much stronger a base, right? So chloride ions are not going to affect the pH. What about the copper plus 2 ions? Talk to me about the solubility of copper hydroxide, copper 2 hydroxide. Yep, you're looking at your solubility rules. What does it say about the solubility of copper 2 hydroxide? They're insoluble. Here's what that means, folks. Look at that if you put copper plus 2 ions along with hydroxide ions, they're going to make a precipitate. Now, here's the thing. If I add copper 2 chloride to water, will we see a precipitate? Well, maybe we will and maybe we won't. It depends on how much we add. But, the fact that copper 2 hydroxide is insoluble tells us that copper 2 ions have a very strong attraction for hydroxide ions, doesn't it? Right? Now in water, there aren't very many hydroxide ions, but if copper and hydroxide have a strong attraction for one another, that means adding copper ion to water will reduce the hydroxide ion concentration. And if you reduce the hydroxide concentration, you raise the hydronium ion concentration, and you make the pH less than 7, don't you? Now, why did this happen? Well, because copper ions are strong Lewis acids. Define a Lewis acid for me. A good acceptor, they don't take or give, right? They actually share, but a good acceptor of unshared pairs of electrons, huh? Electron pair acceptor. And copper ion is very good at that. Now here's the thing. Sodium ions, they're positive. Why didn't we talk about sodium ions being a Lewis acid? Well, when I put sodium ions together with hydroxide ions, what happens? Do we, for instance, make sodium hydroxide precipitate? How do you know? Solubility rules tell you that sodium hydroxide are soluble together. In other words, they're very willing to be separate in solution. In other words, how much attraction does a sodium ion have for a hydroxide ion? Not very much. And we know that from the solubility of sodium hydroxide. On the other hand, how much attraction does a copper ion have for a hydroxide ion? A lot. How do we know that? From the solubility rules. Copper hydroxide is not very soluble in water. Are you with me? So the solubility with hydroxide of a positive ion gives us a hint of how strong a Lewis acid it is. How good an electron pair acceptor it is. And sodium is a crappy electron pair acceptor. What?
You said, same as the Lewis.
So the key is, positive ions can all be Lewis acids, right? Hello?
Yeah.
Now see, writing this down is important. What's more important? No. Make sure that you understand it, right? So you're all being very good about making sure that you get the right words down on the paper. That's good. That's good. But you're not all the way home yet, are you? Right? Now, so listen to what I say and make sure that you understand this. Any positive ion can be an electron pair acceptor. Yeah? So any positive ion could be a Lewis acid. That's our definition. The question is, how good are they at doing that? A way we can judge how strong a positive ion is as a Lewis acid is by how much it attracts hydroxide ions. Yeah? Again, you're writing. Are you making sure that you understand that? How good is a positive ion at attracting hydroxide ions? And what is it that you have that gives you an idea about how strong an attraction a positive ion has for hydroxide ions? Rule number, whatever it is, right? About the solubility of hydroxides.
So we're saying, so it does Na plus OH make us, does it make like precipitate or doesn't it?
If I took a solution of sodium ions, say sodium chloride,
Yeah.
and a solution of hydroxide ions and poured them together, we'd get no precipitate.
Oh, okay.
Now, why is that? Because your solubility rules tell you that it's soluble. That sodium hydroxide is soluble. Huh?
Yeah.
So sodium and hydroxide ions can exist together in relatively large amounts in solution without attracting each other.
So even though you put an S there, it doesn't actually.
Well, you know, I can take sodium ions and hydroxides and put them together in solution and no precipitate will form. But if I evaporate the water away, I'm going to get some solid sodium hydroxide, aren't I? In other words, at some point, the concentration of hydroxides and sodiums gets so high that they do begin sticking to one another, right? But that was our point we made about solubility, that's not like you either are soluble or you're not, right? it was sort of a qualitative thing. We have a bunch of compounds that we consider soluble, we have a bunch of compounds that we consider insoluble. Are any of them completely insoluble? Are any of the soluble ones, does that mean we can never make them a solid in the solution? Of course we can. It's about how soluble they are. The solubility rules don't talk about how soluble they are. For instance, sodium chloride is more soluble than magnesium chloride, but both of